All right then, so let's try another video here. This is going to be about two lessons in here. This is on horizontal asymptotes, and the next one is going to be on oblique asymptotes. So shouldn't take us too long to get through this, but a couple of ideas in here we've seen before already. This idea of horizontal asymptotes, we've kind of worked with this. So it starts off by saying sketch the graph of the function f of x equals 1 over 4x plus 3 and determine the limit as x goes to infinity of that thing graphically. So what do we notice about this thing? Well, we know that it's going to look a little bit like this. It's going to look like, let's try. 1 over 4x plus 3 is going to have a vertical asymptote, we know, at -3/4. Vertical asymptote there. We know that it's going to pretty much look kind of like this and kind of like this. What we dealt with before is we looked at this and we said, if we've got limit as x is going to infinity, 1 over 4x plus 3. If x is going to infinity, then we multiply both numerator and denominator by 1 over x, x being your highest degree of either the numerator or denominator, and we have 4x downstairs, which is degree 1, so we're going to divide just x to the 1, both top and bottom. And then this ends up being equal to, therefore, this is the limit as x goes to infinity of 1 over x over, and we distribute, and this becomes 4, 3 over x. As we take x going to infinity, as we evaluate this limit, this becomes 0 over 4 plus 0, which is, of course, just 0. So what's occurring at infinity? How could we determine this without a picture of the graph? So know that it kind of looks like this, but how could we determine that? Well, we know that we have 1 divided by a very large number, and 1 dividing by an increasingly large number is going to go to 0. And in fact, any constant divided by a increasingly large number is going to go to 0 as well. Next one says, okay, so then what about if we determine the limit of x going to infinity, x squared minus 4 over 3x squared minus 2x plus 1? How can we determine this without a picture of our graph if we have the limit as x goes to infinity? X squared minus 4 over 3x squared minus 2x plus 1. And we are going to multiply top and bottom. Divide top and bottom by x squared and multiply by 1 over x squared. And when we do that, we get the limit as x goes to infinity. What do we have? We are left with 1 minus 4 over x squared. Distribute downstairs, we get 3 minus 2 over x, 1 over x squared. When we evaluate this limit, a lot of this becomes 0. 0 plus 0 ends up being equal to 1/3. So kind of an important piece to this to remember is if our direct substitution yields infinity over infinity, then our step is going to be to divide numerator and denominator by the largest degree of x. Largest degree of x in the denominator, then simplify and attempt direct substitution. So we've kind of seen this before. So remember that horizontal asymptote, the value of a function as x approaches, that the function approaches as x becomes larger, either in the positive or negative direction. That's your asymptote that our function is getting closer and closer to when x gets inherently large or small. And so what that means is if we have the limit as x goes to positive or negative infinity of 1 over x over r, 1 over plus or minus a really big number, this is equal to 0. And in fact, we could actually make this not just 1, but any for any constant k. That would be true. What that limit's going to be is we use capital letter L and we say the function will have a horizontal asymptote at y equals L if either of the following are true. If your limit is equal to limit of fx, x going to infinity, if it's L, and the limit as x goes to negative infinity, if the limit of that is L. What that's saying is we might have the limit going from either or both directions, right? So we might have this horizontal asymptote because when x gets to be very large, it's approaching that. When x gets to be negative infinity, it might be going, might have some other behavior, whether it's going to negative infinity for a y value or whether it's going somewhere else. It doesn't really matter. We talk about this as a horizontal asymptote, and so we label it as a horizontal asymptote. So here y equals L is our limit. Even if it's oscillating where it's above or below, and we have something like this, we are approaching, this ends up being our horizontal asymptote. It can be a negative infinity limit as x goes to negative infinity as we're going further out to the left, and it doesn't necessarily need to be both positive and negative infinity, but it can be. We can have different horizontal asymptotes, whether we go this direction or that direction, and so those are all the different ways that it looks. On top of course, I suppose we should maybe have a picture of just your good old good old limits both to positive and negative infinity that we have approaching the same number. Okay, so to find our horizontal asymptotes, remember that the limit of a constant divided by x to the r as x goes to plus or minus infinity is 0. Divide every term in the function by the highest power of x of the denominator. So we're just going to look at your highest power of x of the denominator. If it's infinity, then there is no horizontal asymptote. So let's just look at your denominator's degree. In this case, we have our limit of f of x. As x goes to infinity equal to the limit as x goes to infinity of 3x squared minus x minus 2, all divided by 5x squared plus 4x plus 1. But we are going to multiply this thing top and bottom over x squared, or we're going to divide by x squared, because that's your degree in the denominator. And when we do that step, this now just ends up being equal to the limit x goes to infinity of 3 minus over x minus 2 over x squared. Just distributing that, this becomes 5 over x plus 1 over x squared. Most of these terms just go to 0 when we evaluate, and we end up with 3 minus 0 over 5 plus 0 plus 0. We get 3/5. Nothing really new here. We've seen this before already. Same thing with this next one. We have a limit of f of x goes to infinity is equal to the limit infinity of x over x squared minus x minus 6. Resist the urge to factor. We're actually doing something a little different here. I know you guys have gotten into the habit as soon as you see something like this, you're like, oh, I can factor that. Let's not do that. We're going to take this approach we're talking about x getting very large numbers. In the numerator, we have 1 over x. In the denominator, we have 1 minus 1 over x minus 6 over x squared. We evaluate that limit. This becomes 0 for 1 minus 0 minus 0. So this is just equal to 0. This last one, I guess technically this rule still works. The denominator is just 1, so the degree of the denominator is 0, so we're just dividing everything by x to the 0, which is just 1. If we think about what's going on here, this is a polynomial. This is degree, I don't know, 5. And so we know as the limit as x goes to positive infinity of this thing, as we go further out to the right, this will be positive. This will be positive, really big numbers. This is going to be a very large negative number. So this ends up being equal to negative infinity. As always, when you have a limit that goes to infinity or negative infinity, that limit does not exist because infinity isn't a number. And so we say that, but we use the negative infinity to help us draw. No horizontal asymptotes in a polynomial function. Polynomial function. Really, that's the guts of it. So we've really we have seen this stuff before, so nothing new here. Okay, this, however, this is going to be new, kind of. Oblique asymptote. So oblique kind of means this, just the same thing as slant, and it's exactly what we kind of think of what that means. What that means is we're going to have an asymptote which ends up being not horizontal or not vertical. And so we're going to deal with that for the first time. Ends up being kind of an interesting thing. And so let's see what happens in here. It says, consider this function 4x squared minus 4x minus 3 over x plus 3. If this is y1, let's use long division to determine your quotient and the remainder. We've seen this before. This has been new. If we do this by long division, 4x squared minus 4x minus 3. Remember that every term, every degree has to be present. And if it's not, then you would call it 0. When we do this, how many times does x go into 4x squared? This would be 4x times 4x times x, 4x squared. We'll do some math. This is no big deal. This is stuff you've seen before. Remember that we're subtracting. This should be minus 16x. Be careful about that. That always seems to hang some of us up. And now how many times does x go into minus 16x? Well, that would be minus 16 times, of course. Minus 16 times x. Minus 16 times 3 makes this negative 48. And when we subtract, be careful about subtracting. This is positive 45. We are subtracting that. We are subtracting. If you'd rather, we can do this. We can do this as synthetic division. We call it negative 3 because negative 3 would be the value of x that makes that 0. And so we write down our coefficients for negative 4, negative 3. We have to be careful about this. This will only work if this is a 1x here. If, say, it was 4x plus 3, we would have to do, there are some steps we could take to modify our process. We're not going to get into that for now. For now, we're just going to do it this way. And so our 4 comes down, we multiply, negative 3 times 4, negative 12. We add down is negative 16. We multiply, we get 48. We add down, we get 45. Now, what this all means, a little bit of terminology. Q of x, 4x minus 16. What part was 4x minus 16? What was this? What was this? That was what was called the quotient. R of x, which is this part here, at 45. R of x is 45. The word for that is called the remainder guys know those, that's not a big deal. N of x, which was this original numerator, 4x squared minus 4x minus 3. It's the part that we are dividing into. It is called the dividend. And then the last piece, this x plus 3, is what we divided by. We'll call it d of x. Our word for that is the divisor. So we have some terminology that we will use occasionally with this. What this all means, and if we kind of back it up and think about what happens if we had something a little simpler. Say we had, let's see, 31 divided by 9. Well, we know that 31 divided by 9 is, and if we did this as a long division, it would go into 27 3 times, and we'd have a remainder. Of 4. So way back in elementary school, we called this 3 4/9 as a mixed fraction, because 3 is your quotient, 4 is your remainder, and 9 is your divisor. So if we think about it that way, the same thing goes on with this. So 4x squared minus 4x minus 3 over x plus 3 can be written as 4x minus 16. There's your quotient. We had a remainder of 45 over our divisor of x plus 3. Now, if we're comparing the values of y is equal to 4x squared minus 4x minus 3 over x plus 3 to just what happens with this part, with that polynomial part, if this is 4x minus 16 is this second function that we're just going to call y2, as x approaches positive or negative infinity. Let's see what we get when we are going to calculate these. So we've got a table of values, and we're going to plug negative 10 in for x. And so negative 10 in for x, you should get negative 62.43 for our first function. For our second function, 4 times negative 10, negative 40 minus 16 is negative 56, it looks like. I'm going to let you go through this and complete this table. I'll meet you back here in just a second. All right, so hopefully you get some values that kind of look like this. The point is what's going on is when x gets to be very large negative or very large positive numbers, the further you go to the left or the further you go to the right, notice that either way use just the quotient, or if we use the whole function, we end up getting values that end up getting closer and closer to each other, right? So we have the further out to the right that we're going, 184.84 is getting closer and closer to our y2 value. And by the time we get to 1,000, a couple of decimal places is how they differ by, and the further to the right you go. So that's kind of our definition of what an asymptote is. It's a line that our function is getting closer and closer to as x increases. So therefore, what we can say about our values in y1 relative to the values of y2, as x goes to positive and negative infinity, we would say as x goes to plus or minus infinity, the values of y1 approach the values of y2. You're getting closer and closer to that, so it ends up being less and less significant. And if we take the limit as we go to infinity, it actually ends up being the same. What our graph ends up looking like is our graph of y1 is this blue line. Our graph of y2 is this linear function, of course. And so as we get larger, it gets closer and closer to an end. It approximates it. And as we go to infinity, it actually equals that. Values, not large values of x. So like right here, they look very different. We have very different y values. But as we get, as we go far enough to the left and to the right, it approaches this. This is called an oblique asymptote. also known as a slant asymptote because it's just this slanted line. It's, in mathematics, we call it an oblique line. An oblique line is a new non-horizontal line which the graph approaches as x goes to plus or minus infinity. All right, so not that big a deal. So all that we need to do is remember that to look for oblique asymptotes, we just have to do some division and look at what we have for a quotient. So why does it approach this? Knowing that y1 can be expressed as y2 is just like this, then why does the graph of this approach just this 4x minus 16 part? Why is it just this? That's kind of inferring that this part's irrelevant. Well, that's kind of what we were just looking at a few minutes ago, is because the limit as x goes to infinity of 45 over x plus 3, divide top and bottom by 1 over x. And this will be the same thing. The limit as we go to negative infinity, they are both equal to 0. Why are they not close when x is 3? Well, we do have a vertical asymptote. We have a vertical asymptote on y1. What is our vertical asymptote equal to? Well, it's negative 3. Our limit of y2 as x goes to negative 3 actually ends up being equal to negative 28. Whereas the limit as x goes to negative 3 on y1 is any doesn't exist. It's plus or minus infinity, right? All right, so just to sum this up, our equation of the oblique asymptote, going to use long division to find your quotient. That ends up being the critical piece, is we're trying to look for the quotient, use long division or synthetic division. Long division is probably a more powerful tool because it works in places that synthetic division doesn't. This is your equation of your oblique asymptote. It may exist for a rational function when the degree of the numerator is greater than the degree of the denominator. Okay. It's worth noting, last piece is it's kind of interesting. You can have, they don't have to be straight line asymptotes. You can have other polynomial shapes of asymptotes that you're approaching. So you might be approaching a quadratic or whatnot. So check that out if you'd like. And there it is. Thanks so much, and good luck to you today.